Okay, so Gij with the lower indices is a 3 by 3 square matrix in 3 dimensions in 3D. So the inverse matrix in 3D, it is again a 3 by 3 square matrix, which is the inverse of the above matrix. And the elements are represented by Gij. So I have a square matrix and I have an inverse of that matrix. If I multiply these two matrices, I should get the identity matrix. Okay. So if I matrix a square by its inverse, I should get the identity matrix. So in terms of Gij, it is written like this. Gij, Gjk. Okay. This is Ij, then this J is contracted over Ik. This is equal to delta Kronecker delta Ik. Okay. So this is how we write it in the tensor form. Gij, Gjk equal to delta Ik. So that means if I is equal to k, it is 1. If I is not equal to k, it is 0. That means it is an identity matrix. So this delta Ik actually represents an identity matrix. So it is symmetric matrix. So the position of k and I, that amanabu halasu, you can write k before I or k after I, doesn't matter. And as we said, this, since the metric tensor is defined in terms of the dot product of two vectors, it is also a symmetric matrix. So Gij is equal to Gji. Similarly, this contravariant Gij, it is also a symmetric matrix. Okay, because we have the metric tensor Gij in 3 dimensions. It is a 3 by 3 square matrix, which is symmetric. So this square matrix will also be symmetric. And if you take the inverse of a symmetric matrix, then the inverse will also be symmetric. That means Gij is also symmetric. Okay. So if we look at this, then from the quotient rule, we can see that Gij is a second rank contravariant tensor. Contravariant tensor. Okay, this is clear. Okay, then next, let us move to raising and lowering of indices. Raising and lowering of indices by using the metric tensor. So if Vi is a contravariant vector, okay, I repeat, if Vi is a contravariant vector, then we can create a covariant vector by multiplying this Vi with the metric tensor and then contracting over one index. So how can we create a covariant vector? Let us see. So Gij, Vj, this actually gives us Vi. So this Vj, this upper index, when I multiply it with by the metric tensor, covariant metric tensor, and then contract over the index j, we get Vi. This is how you lower the index, and this Vi is actually a covariant vector. Okay, you can see very easily by using the quotient rule. There you go. So this is how indices is lowered by using the metric tensor. Similarly, we can also raise the indices by using the contravariant tensor, metric tensor. So suppose I have Vj, and I multiply it by Gij. This is a contravariant metric tensor. Okay, then this will give us Vi. Okay, so here J is also contracted over. So this process of finding the contracted product of a vector with Gij is called this lowering of index or raising of index. Okay, and sometimes we say that these vectors Vi, this contravariant vector Vi and covariant vector Vi, sometimes we say that they are the contravariant components and the covariant components. They are the contravariant components and the covariant components of a vector V. Sometimes we say like this. I repeat, this Vi, these are the covariant components of the vector V, and this V with a superscript I, these are the contravariant components of the vector V. Sometimes we say that, okay, but I prefer not to use that term here. Okay, this is fine. So let me take a new sheet of paper.
Sir.
Yes, yes.
Sir, sige. Index.
So a vector toward minor from a general tensor. This is suppose T, I, J, K. This tensor, which is a mixed tensor, it can be written in various different forms by raising and lowering indices using the metric tensor, and we can obtain from this, we can obtain T ijk, and we can also obtain T ijk. We can also obtain T ijk. Metric tensor toroga raise and lowering going to we I say, for example, if I want to start with this and come to this, what do I do? T I J K. So I want to bring this upper index I to the lower index. Okay, then let us use the metric tensor. Okay, so this I, since I want to bring it lower, this should be summed over. So aduna kari harasige. So A I. See which index is repeated? The index I is repeated and it is summed over. So this will give us, this is equal to T I will, this I will be replaced by A J K. Okay, so this is how you lower index. Sidana A label fasade, sidana I lere, sidana A lere fasade. If you want I here, then you can do one thing. Write it as T L J K, like this, I L. Then this there L will be summed over and you will get T I J K. Okay, this is fine. So we can obtain this from this. Similarly, from this you can obtain this by multiplying by the contravariant metric tensor 3 times. 3 times. So all these tensors, I repeat, all these tensors in various different forms formed by raising and lowering indices by using the metric tensors, these are called associated tensors. Associated tensors. Okay, and as I mentioned earlier, the electromagnetic field strength tensor F mu nu. Then we can have F mu nu like this, and then we can have F mu nu. These are also associated tensors. One can be obtained from the other by using the metric tensor to raise and lower indices. So these are also associated tensors. Okay. Then one last point. Take a new sheet of paper. Let us remember the line element again. ds square equal to gij dxi dxj, where gij is ai dot aj. So if I want to draw the diagram, let me use a different color here. So I have a point P here. The three axes may be like this. Okay, this is the x1 axis. This is the x2 axis. This is the x3 axis. Sorry, x3 axis. Okay, at this point, what is the direction of A1? A1 is directed along this. So this is A1 vector. What is the direction of A2? A2 is directed along this. This is A2 vector. What is the direction of A3? A3 is directed along this. So this is A3 vector. These are the tangent vectors to the x1, x2, x3 curves at this point P. Okay, this is fine. And we saw that this is actually 9 terms in 3 dimensions. 9 terms in 3 dimensions. That's wrong. So is it still there? I don't know. Oh, no, it's not there. Okay, no problem. 9 terms in 3 dimensions. And if we remember our Euclidean geometry in 3 dimensions, what is the if we use the rectangular coordinates, that is the Cartesian coordinate systems in 3 dimensions, this equation, this line expression for line element, it reduces to the distance between 2 points is given by dx1 square plus dx2 square plus dx3 square. This is actually in our Cartesian coordinates, this is actually dx square plus dy square plus dz square, ds square. So this is what we learned in our Cartesian coordinates in Euclidean space in 3 dimensions. That's right. Is it clear? Are you getting the point?
Oh, sir.
Okay. Now, if you compare this equation and this equation, so you take this equation and this equation. This means g11 dx1 whole square plus g22 dx2 whole square plus g33 dx3 whole square. That's wrong. So dx square is nothing but dx1 square, dy square is nothing but dx2 square, dz square is nothing but dx3 square. So the Euclidean space, in the Euclidean space in 3 dimensions, if we use the Cartesian coordinates x, y, and z, then this 9 terms, the 9 terms reduces to only 3 terms. And this g11 is actually 1. We have 1 here. G22 is actually again 1. G33 is again actually 1. Okay. And what about the cross terms? Here we had cross terms like dx1, dx2, dx2, dx3. So we had terms like this. We had terms like this. G12, dx1, dx2. We had terms like this, cross terms. But what is G12? G12 is actually A1 dot A2. In Cartesian coordinates, the tangent vector along the x-axis and the tangent vector along the y-axis, they are perpendicular to each other. That is, our Cartesian coordinate system is an orthogonal system. Okay, orthogonal curvilinear coordinate system. So for orthogonal curvilinear coordinate system, these dot products are zero. So the cross terms, they do not appear. Cross term because G, the component of the metric tensor, is zero. So out of those 9 terms, the 6 cross terms, they vanish, and the 3 terms, which are the diagonal terms, they remain. So in matrix notation, Gij for the Euclidean space in 3 dimensions is nothing but 1, 0, 0, 0, 1, 0, 0, 0, 1. This is for Euclidean space. Euclidean space 3D. This is the 3D Euclidean space in Cartesian coordinates. In Cartesian coordinates. So what I want to say is that if our coordinate system is orthogonal, that is, if the basis vectors are orthogonal, okay, then the 9 terms reduces to only 3 diagonal terms. And one speciality of the Cartesian coordinate system is that the values of the metric tensor GII, or the diagonal elements, they are actually 1. 1, 1, 1. Because here we already saw it is 1, it is 1, it is 1. So is this clear, or is there any difficulty here in this particular concept?
Oh, yeah, sir.
Okay, everything is fine. So this is clear. Now, if from my rectangular Cartesian coordinate systems, if I shift to spherical polar coordinate systems, okay, if I shift to my spherical polar coordinate systems, in such a case, so spherical polar coordinates. Spherical polar coordinates, then x1 would be r, the second coordinate curve would be theta, and the third coordinate curve would be phi. Now recall, in such a case, we still have this equation for a line element. Why? Because the spherical polar coordinate system is again an orthogonal coordinate system. That is, the dot product of the cross terms. That is, the dot product of the basis vector along r and the basis vector along theta is 0. It's an orthogonal coordinate system. So out of those 9 terms, we have only 3 terms. The 6 cross terms will vanish. Okay. But for spherical polar coordinate systems, G11, G22, and G33 are no longer 1. 1 day will recall. They will no longer be 1. Okay. They will no longer be 1. G11 is not 1. G1, so G22 is not 1. G33 is not 1. Oh, sorry. In this particular case, G11 is 1. So let me cancel this. G11 is 1. But G22 is actually r square. And G33 is actually r square sine square theta. So in general, the components of the metric tensors are not 1, even in Euclidean space. Even in Euclidean space, if you use spherical polar coordinates, the components of the metric tensors are in general not 1. Okay, the components of the metric tensor are 1 only if you use Cartesian coordinates in Euclidean space. Okay, so I'll try to make one video which shows that these metric components are not one. So I'll try to make one video for this. Now let us move to the last topic, that is the space in special theory of relativity. Okay, so let me take a new sheet of paper, change the color. Okay, this in special theory of relativity, we learned that space, time, we should combine space and time together and say space-time, and space-time is four-dimensional. In special relativity, space-time is four-dimensional. Space-time is four-dimensional. Okay, and that is called Minkowski space. Minkowski space. Okay, here I am saying space-time, and here I am saying space. So what is the meaning here? In the word space in Minkowski space. So the word space here actually means a vector space. The vector space which you learned in your linear algebra. This is a vector space. So let us see what Minkowski space is. I'll stop sharing and I'll share my page. Okay. So let me share. Can you see the website? This is the Wolfram Math World website. And you can see that Minkowski space here. So Minkowski space is a four-dimensional space possessing a Minkowski metric. And what is a Minkowski metric? Minkowski metric is actually a metric tensor having the form. Here the line element is given by this form. Okay, the line element is given by this form. Okay, so let me come back to my whiteboard. Okay, so in Minkowski space, in your classes on special theory of relativity, you must have learned that ds square is actually c square dt square minus dx square. Sorry, dx, it should be dx1 whole square. So let me undo this. So it should be dx1 whole square minus dx2 whole square minus dx3 whole square. Or you might have written it like this. This c dt, if you write it as dx1, dx0, sorry, this is actually dx0 whole square minus dx1 whole square minus dx2 whole square minus dx3 whole square. This is ds square. And if you compare it with the expression for the metric tensor, this is gij dxi dxj. Okay, so you compare this equation with this equation, and what do you get? We get g00 equal to 1, g11 equal to minus 1, g12 equal to minus 1, g1, sorry, this would be g22, g33 equal to minus 1. So here, the coefficient here is actually g00. The coefficient here is actually g11, the coefficient here is actually G22, and the coefficient here is actually G33. And since it is 1, 1, 1, sorry, minus 1, minus 1, minus 1, we have minus 1 here, minus 1 here, minus 1 here, and the coefficient here is 1, so we have 1 here. So in matrix form, this is written as Gij. This is a square matrix: 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. This is called a Minkowski matrix. Sorry. METRIC, Minkowski matrix. Okay. And this is true. This is true only when you are using x as dx1, y as dx2, and z as dx3. So here, let me use the pointer spotlight. So here dx1, the dx1 here where you are using here is actually x. This dx2 is actually y. This dx3 is actually z. So this coordinate system, let me draw a box here. This coordinate system is called the Galilean coordinate system. Galilean coordinates. Galilean coordinate system in the book Classical Theory of Fields by Landau and Lipschitz. Landau and Lipschitz. Galilean coordinate system ko. So the metric, let me use the spotlight. So the metric tensor Gij has this form when you use the Galilean coordinate systems in Minkowski space. So Minkowski space की metric tensor दी करी form the lay, Minkowski space की metric tensor दी she forms the lay. Let me use the box here. So the Minkowski space की metric tensor दी she form the lay if you use the Galilean coordinate system. But instead of the Galilean coordinate system, if you use the spherical coordinate system, then the form of the metric tensor will change. Okay. Yarba. The components of the metric tensor will change. Why? Because when we change the basis vectors, the components of a tensor change. So if we are changing the coordinate system, we are changing the basis. So when we use a different basis, the representation of the tensors will also change. That is, the components of the tensors will also change. But this is what you learned in your special theory of relativity, that the metric tensor has this form. And I want to emphasize the point that the metric tensor of the Minkowski space has this form only when you use the Galilean coordinate system. That is the rectangular coordinate system. So I'll pause my recording. Okay. So Minkowski space is the flat space-time of the special theory of relativity, where there is no gravity present. If you want to introduce gravity, then the space is called the Riemannian space. Riemannian space Korani. Then even though we use the Galilean coordinate system, Riemannian space the metric tensors is form the later. The metric tensor will no longer be of this form. The metric tensor will change if we change the space from Minkowski space to Riemannian space, and then the metric tensor will change even though we use the Galilean coordinate system. And that metric tensor, it contains all the information about the curvature of space-time. Okay, so that's all I wanted to say here. I'll stop the recording.